chapter 2, which is on permutations and combinations is the name of the title, the chapter. It's also called combinatorics, and basically these are counting problems. I know counting, that sounds encouraging. Wow, counting, I mastered that a few years ago. It's a little bit more difficult counting. This is counting like how many ways can you arrange 16 books on a shelf? Or how many ways can you arrange 16 books on a shelf if the first book has to be a romance novel and the last book has to be a mystery or something like that. They can get really complicated. So a lot of these sort of questions rely on something called the fundamental counting principle, which is the name of the first section here. I'm going to come back to that in a second. I'm actually going to start right away with this question, and we're going to solve it two ways. First, we're going to solve it with a tree diagram, which you did in grade 8, and then we'll try it with the fundamental counting principle. Okay, the question is, Hannah plays on her school soccer team. The school uniform has three different sweaters. The sweaters are either red, white, and black. And 3 different shorts. The shorts are also either red, white, or black. How many different versions of the soccer uniform are possible? Now, one way you could answer this actually is you could make a table for yourself. I'll just do that over here. So you could do something like, here's the sweaters, here's the shorts, and it could be a red sweater and a white red sweater and a red shorts, or it could be red sweater and white shorts, or it could be red sweater and black shorts, or it could be white sweater and red shorts, or it could be white sweater and white shorts, or it could be white sweater and black shorts. Is that all of them? No, it could be black sweater and red shorts, black sweater and white shorts, black sweater and black shorts. These are all the combinations. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 different possibilities. Okay, that's one way you can do it. You could just list them all like this. Another way that you could use is a tree method. So this is actually kind of method 2. Here's method 1 over here, and are just listing them all. As I said, you did this in grade 8, and it gave people fits in grade 8. It always does, and it continues in grade 12 when I teach this to just be a real nemesis for some people. So what you're going to do for a tree diagram is you're just going to start by making a dot. And then you're going to draw from there your first thing you're going to consider. Now, the reason most people get this wrong is because they do this. They consider sweaters, this is wrong, don't write this, and shorts. But that's not true. You want to start by just considering either sweaters or just considering shorts. So let's start with the sweaters. So what I'm actually going to do is I'm going to write sweaters up here. And if we just think of sweaters, how many different possibilities are there? Well, it says right here there's 3 different types of sweaters. So I draw 3 lines coming out of the point. 1, 2, 3. And what kind of sweaters are there? There are red sweaters, there are white sweaters, and there are black sweaters. Great. So if Hannah was just picking her sweaters, she could either pick a red one, a white one, or a black one. Now what we have to do is we have to consider her shorts. Okay, let's first of all assume that we're following this pathway, that Hannah's picked a red sweater. How many shorts could she pick, assuming she's picked a red sweater? Well, the red sweater has no impact on which one of the shorts she can pick. She can pick any one of the 3. So that's why coming out of here, you should have 3 lines. And what would each one of these lines say at the end of it? It would say red, white, and black, because that's the sort of shorts that Hannah could pick. Okay, here's another possibility. What if Hannah actually picked her white sweater? What kind of shorts could she pick then? Well, again, the color of the sweater doesn't impact. She'd still have the same choice. She could either pick red, white, or black. So again, red, white, black. And finally, what if Hannah picked her black sweater? Well, then she still has the 3 same choices for her shorts. She can either pick red, white, or black. And where you look to see how many different versions there are of the soccer uniform, just look at the end here and you see how many pathways there are. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9 pathways. So again, we get that our answer is 9. Got it over here, 9, got it over here, 9. Now let's be clear what each of these are. This first one right here, what's the pathway? Like what is this combination here? This is red sweater, red shorts. What's this one here? White sweater, white shorts. What's this one right here? This is black sweater, red shorts. Okay? And you can use this to figure out different things. If I asked you how many of the combinations do not involve the same colored sweater and shorts. So then you wouldn't count red red, you would count red white, red black, white red. Don't count white white, count white black, black red, black white, but don't call black black, count black black, so you're left with 6. There's 6, they don't have the same colors. Okay, you can do all sorts of things with this, but it relies on you being able to draw a tree diagram, and as I said, some people really struggle with that. But it always works the same way. Start with the dot, start with one thing you're considering, and then the next thing you're considering. And if there's even more things you're considering, you just make another column after that. Alright, now both those methods are pretty good, but they take quite a bit of time. It'd be nice if we had a faster method. So there is a faster method, and it's the fundamental counting principle. So I think it might be even easier to look at this first method to come up with the fundamental counting principle. Do you notice what I did is I started with the red sweaters and I put red red, red white, red blue, or black, sorry, red red, red white, red black. And then I did white red, white white, white black. And then I did black red, black white, black black. So do you see that every time I picked one of these first 3 colors, red, white, or black, I then had 3 options with it, right? When I picked red, I had 3 options for it. When I picked white, I had 3 options for it. When I picked black, I had 3 options for it. Now, my initial choice of sweaters, I also had 3 options for that too. 1, 2, 3. So what I effectively had is a first choice out of 3, and then a second choice also out of 3. So this is the fundamental counting principle. I will now write it up here. The fundamental counting principle states, if one task can be performed in A ways, that's an A is a number, right? Another task can be performed in B ways, that should say ways, not way. I hate it when I do this, but that should say ways there. Another in C ways, and so on. It could be another in D ways, another in E ways. Like, you just do as many as the tasks you're talking about. Then all these tasks can be performed in A times B times C times D times E times however many you need to do ways. So, for example, in this question here, I guess what I could have written is N for the number of different outfits you could wear equals the number of sweaters times the number of shorts. And in this case, the number of sweaters is 3, red, white, black, and the number of shorts is 3, red, white, black. 3 times 3 is 9. That's it. It worked. 9, 9, 9. We did it 3 ways. I'm pretty sure of this answer. Okay, the fundamental counting principle just involves multiplying things together. This example that we just considered was when Hannah wanted to pick a sweater and shorts. So anytime you have a question, any example that involves and will require multiplying to get the total number of arrangements. And that's all we're going to do today, are questions that involved and or multiplying. However, next day we're going to start working with questions that involve or. And when you have an or question, you actually will do some adding, and we'll look at that next time. Okay. Also, one other thing, sometimes there's restrictions. I'll show you what I mean in a second. And the rule with restrictions is deal with the restrictions first. Okay, so I'll show you in just a second. So here we go, a bunch of examples. A luggage lock opens with the correct 3-digit code. You know what I mean? It's like a bunch of dials that you spin, and you have to get the right 3 numbers in order for it to open. So these wheels or dials rotate through the digits 0 to 9. How many different 3-digit codes are possible? So what you want to do is you want to think of each of the numbers you're dealing with one at a time. So let's say this is our 3 dials here, right? And we have to spin this one to the right number, this one to the right number, and this one to the right number. Now, we can pick any of the digits from 0 to 9. How many digits is that, by the way? That's 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is actually 10 digits. 1 to 9 plus 0. Okay, so how many different choices do we have for the first dial when we spin it? We could spin it into any of 10 positions. How many choices do we have to the second one? Well, we're using exactly the same numbers. You could put it into any of 10 positions. And how about in the third one? Any of 10 positions. So how would you figure out how many there are? You would do 10 times 10 times 10 equals 1,000. There's 1,000 different combinations that are possible with this 3 wheel lock, or whatever you want to call it, 3 dial lock. Okay, how many different 3-digit codes are possible if each digit can only be used once? Can only be used once in the code. Yeah, you can only use it once, so this is a little bit different. So I'm going to draw the same thing. Now, you start with the first dial, that you can pick any of these numbers, right? We have 10 to choose from. Now, we don't know which digit this is, But whether this is a 5 or a 7 or a 2 or 0, whatever, since they can't repeat, how many choices do you have for this one? You don't have 10 anymore. One of them's been used right here. We don't know which one it is, but there's definitely one number that shows up here and it can't be repeated. So therefore you can't have the same number here. So you don't have 10 numbers anymore to choose from. You only have 9 numbers to choose from, 9 digits to choose from. Okay, similarly here, once you get to this one, you've already used 2 different numbers. So you don't have 10 to choose from anymore. You only have 8 to choose from. And the way you get the answer is 10 times 9 times 8, which is 720. That's the number of different. It makes sense it would be less, right? Here there's no restriction. This is a question with restrictions. Now we didn't really follow the rule, which I just gave you in the page about doing the restriction first. But the next question is another restrictions question, and this one I really do think it's worth your while to do the restriction first. The question is, how many even 2-digit numbers are there? Okay, so 2-digit numbers are like 23, 85. What's the biggest 2-digit number? 99. What's the smallest 2-digit number? 10. Okay, this is not a 2-digit number. I mean, I suppose you could argue it is, but we're not going to say that's a 2-digit number. That's a 1-digit number. It's just 8. So the smallest 2-digit number is 10. The biggest is 99. We want to know how many even numbers there are between there. Now, it wouldn't be too hard to do this with just counting them in your head or something. But let's say this is how many even 6-digit numbers. That'd be a lot harder. So it's good to be able to do this without counting one after the other. So we want a 2-digit number. Here's my first digit. Here's my second digit. It says even here. So because it says even, we have a restriction. Which number do we have a restriction on? We actually have restrictions on both of them, to tell the truth. But because it says even here, which number does that impact? That impacts the second number. The second number there has to be one of which numbers? It could be 0, because numbers ending in 0 are even. It could be 2, it could be 4, it could be 6, it could be 8. So there's 1, 2, 3, 4, 5. There's only 5 numbers to choose from here. Okay? Now in the first one, which numbers could it be? Well, first of all, repeats are okay. So it could be any of the numbers here, even if it was like a 6 that was in this spot, could still be a 6 here. Remember, this 5 doesn't mean the second digit is a 5. It means there's 5 digits it could be. So is there any number it couldn't be in this first one? Yeah, there's one number it couldn't be. It could not be 0. No 0 here. So because there's no 0 there, but we have 9 other digits, there's 9 possible numbers it could be. 9 times 5 is 45. There's 45 2-digit even numbers. How many 2-digit whole numbers can be formed using the digits 0, 2, 4, 6, 8 if repetitions are allowed? Okay, when repetitions are allowed, it's always a little bit easier. We need to make a 2-digit whole number. 2 digits. Even though you have 5 here, you don't need them all. You're only going to pick 2 of them, and repetitions are allowed. So, first of all, is there any restriction in this question? Yes. The restriction is just like that we did up here. You can't start the 2-digit number with 0. Okay, right here there can be no 0. Otherwise, you really only have a 1-digit number. So because you can't have a 0 there, how many numbers can you choose from here? 1, 2, 3. Only 4 of the 5. So this is 4. And the second number, repetitions are allowed, so it doesn't matter. There's no restriction here. It can be any of these numbers. So it can be any of the 5. So you get 4 times 5 equals 20. There's 20 2-digit whole numbers using those digits there. Okay, what if repetitions are not allowed? So we'll start the same way. We'll look at the first one first because there's a restriction on that. There's actually a restriction on both, but we'll start with this one first. And again, it has to be 2 digits, so this can be no 0 here. So how many does that leave? That leaves 4. Now, the second number here, how many digits are left to choose from here? Well, the first number wasn't 0, but it was definitely one of these ones. And it doesn't really matter which one it was of those. Let's just say it was the 6. If we already used the 6, how many are left to choose from for the second number? 4. And again, it doesn't matter which one I choose, it'll always be the same. If it was the 8, if the first number was an 8, how many are left to choose from? 4. So you can't repeat the first one. That means you don't have 5 anymore to choose from. You only have 4 to choose from. You only have 16 here. Which makes sense, right? If you look, there's 4 different here. Why is it 4 different? What are the numbers that would work here when repetitions are allowed, but wouldn't be allowed here when repetitions are not allowed? You'd be allowed to have 88 here, but not there. You'd be allowed to have 66 here, but not there. You'd be allowed to have 44 there, but not here, and allowed to have 22 there, but not here. How about 0, 0? No, we already said that's not a 2-digit number. It's kind of like, I guess it's a 1-digit number, 0, but you don't want that one. Okay, so those are the 4. That's why this one's 4 less than that, is because of these guys here. Alright, BC license plates are made up of 3 numbers and 3 letters. How many different license plates could be generated in this model? So we have 6 spots. 1, 2, 3, 4, 5, 6. And the first 3 are numbers. The second 3 are letters. And it looks like there's no restrictions here, right? It says 3 numbers, and I guess even the first one can be 0. It doesn't matter. So how many digits do you have to choose from in the first one? 10 times. How many digits in the second one? 10 times 10. There's no restrictions here. Letters. So how many letters are there in the alphabet? 26. So you can pick any of those 26. There's no restrictions, so any of those 26 again, and any of those 26 again. You're going to multiply all that together. Now, this is the thing that makes these questions so difficult. You often get these enormous numbers, and it's really hard to get a sense of whether you've done it right. So what this multiplies out to, if you do the multiplying, is 17,576,000. What do you think? Does BC need new license plates anytime soon? Don't think so. I think we're going to be safe for at least a few more years yet. Now, this isn't the case, but what if the numbers cannot start with 0 and the letters cannot repeat? So here we go again, the same 3 and 3, where the first 3 are numbers and the second 3 are letters. And the restriction this time, the restriction is the numbers cannot start with 0. So in this first spot right here, there's no 0. So how many digits are there that can go in that spot? 9. Now, repetitions are okay with the numbers. So even if this is a 5 here, for example, the first number, it can still be a 5 there. In other words, how many numbers do you have to choose for in the second one? 10. There's no restriction. It can be anything. How about the third one? 10. It can be anything. It doesn't matter. Times. Okay, the letters. The only thing it says about the letters is they can't repeat. So the first letter here can be anything, and you know there's 26 letters. But the second one can't repeat this one. So you're down a letter. It wouldn't be 26 anymore. It would be 25. And once you get to this one, you're down 2 letters. It can't be this letter, it can't be this letter. That's 2 gone, so you're left with 24 letters. If you multiply all that out, it comes to 14,040,000. And you'd expect it to be smaller because you put restrictions in. Whenever you put restrictions in, it's always going to make it a little bit smaller. Or, I mean, 3.5 million smaller is, I guess, quite a bit smaller. There you go. This will probably involve a little struggle at first, but keep working at it and you'll get it. We're going to do this lesson in 2 days. We'll do some more difficult ones next day. I'm purposely taking a little bit slow so you don't get too frustrated in the first day of this chapter. Alright, thanks. Take care.